let's now look at the action potential, and for the action potential to actually happen, there are two things happening. One is depolarization and the other is repolarization. Now, before that, when we had discussed about resting membrane potential, that was the polarized state. So now we have to move to the depolarized state. Now, if you remember the scenario, inside there were potassium ions, outside there were sodium ions, correct, in the extracellular fluid. Now, please concentrate on the diagram that comes up here for your better understanding. Now, whenever a threshold stimulus is applied, what will happen? The beginning of the nerve impulse will take place. Now, what is that? Because of the excitation, the voltage gated channels are opening. Now, you can see there are two channels over here. One is a sodium channel and one is a potassium channel. Now, I had told you that at one particular time, only one type of ions can enter or exit. So, here you can see that as the threshold stimulus is applied, the sodium ion channels have opened and there is a rapid flow of the sodium ions from outside. Alright, what they are showing here is nothing but the interiors of the axon and outside it, okay, the extracellular fluid where the axon is placed. Then the movement of the sodium ions inside is happening at a very fast rate. Now, because of that, what is happening is the positivity inside will increase. Earlier, the scenario was interiors were negative. Now, not in the first instance, but throughout the axon length, this will happen one after the other. Alright, and because of the rising of the positivity or the positive electrical signal, the next adjacent sodium gates are opened. Alright, it is because of the change in the electronegativity, correct? So, the changes in the electrical difference is going to initiate the opening of the further sodium gates, which are the voltage gated ion gates, correct? Now, as the sodium keeps on entering inside, there is a shift of the charges. Inside it will become positive and outside it becomes negative, and that is the depolarized state. Alright, so let us write down. When the threshold stimulus is applied, the voltage gated sodium channels, sodium ion channels open and there is an inflow, alright, influx of sodium ions from the extracellular fluid, okay, to the inside. Now understand, the membrane here is of utmost importance because whatever changes are happening, it is happening at the length of the membrane, and so the difference across the membrane is responsible for this change, and it happens here because the ions are densely populated in this particular path, alright, inside the axons as well as in the extracellular fluid, but they are very, very dense here. The ions are very, very dense here, and the way they have depicted the positive and the negative sign shows that the accumulation of the ions are just very close to the membrane, very touching the membrane or adjacent to the membrane. Then, now the rapid flow of the sodium ions inside will then, what it will happen, there is a difference in the local electric potential. Alright, so to the inside, as a result, there is a local electrical potential difference, and you can see that it goes like a wave. All right, the positive charge inside keeps occurring faster throughout the membrane, so that brings about the local electrical potential difference, and the negativity is wiped out, or the electronegativity is wiped off. Then the interiors inside, it has turned now positive, and outside it is now negative. Now because of this, and now the wave of action potential has passed through, the changes has happened. Inside it has become positive, outside it has become negative. That is going to initiate the opposite process, because the depolarization has occurred, the action potential has done its work. Now the neuron has to come back to its normal state. Alright, this is the way it will reach till the axon endings, and then whatever changes will happen there, that we will see later, but this is how the changes has happened. The action potential is created, which is the action potential is created, which is how much? 55, and it is positive, 55 millivolts. You remember there was negative charge inside, that was minus 70, and now the inside has turned positive, and that is the action potential that can be measured. It is positive, so plus 55 millivolts. So this is how the action potential is now moving further, and it keeps happening in the adjacent parts of the axon till it reaches to the place where it has to reach to. So that is depolarization. Following depolarization, what will happen is exactly the opposite, that is repolarization. Now here the process will be exactly opposite, but how it is brought about? Because of the increased positive atmosphere inside, the sodium gates will now close and the potassium gates will open, and now the potassium ions will start moving, and that will bring the neuron, the activated neuron, back to its rest, and that is repolarization, exactly opposite of depolarization. Now between these two, there is a process. Now this entire process, it takes place, the entire process takes place between, don't be surprised, between 1 to 5 milliseconds. Alright, and so we don't even realize what is happening. The nerve impulse goes, comes back, and the action is actually brought about. So the entire process takes place, entire process of depolarization, action potential and repolarization will take place between 1 to 5 milliseconds. And then comes, after this comes a refractory period. Alright, so what is the refractory period? Refractory period just after a nerve impulse has passed through, no stimulus will be able to excite a neuron. All right, it's kind of taking rest before the next impulse comes, and that period is refractory period. It is about 1/1000th of a second in a large myelinated nerve fiber. All right, of a second in a large myelinated nerve fiber. All right, what it is? The inactivity of a neuron in spite of being stimulated by a stimulus. All right, so that is the refractory period. And then there is something called as saltatory conduction here. Saltatory conduction. Now this word is taken from a Latin word of saltare. So saltare means to hop or to jump, and this has shown that the nerve impulse is faster in myelinated nerve fiber. Now what happens is the myelin sheath actually insulates the entire axon, but there are certain constrictions where the myelin sheath is coming closer and almost not there, which is at the nodes of Ranvier. Now at that nodes of Ranvier, there is no myelin sheath, and so the signal's action potential will jump from one node of Ranvier to the next adjacent node of Ranvier, and that is how it fastens up or quickens up the process of the nerve impulse, and that is the saltatory conduction. So what is saltatory conduction? The jumping of the nerve impulse from one node of Ranvier to the next. All right, and can you imagine the speed it can achieve because of this myelinated nerve fiber? Up to 120 meters per second. That is the speed taken up in the myelinated nerve fibers. We can mention it here. It goes as much as up to 120 meters per second. All right, and in case of the even when you talk in terms of the spending of energy by a neuron, the myelinated nerve fibers are much economical because of this saltatory conduction, hopping conduction, and less amount of energy is wasted. Whereas in the non-myelinated nerve fiber, what will happen? The action potential has to go throughout the length of the axon, whatever would be the length, and that much of exchange of this sodium and potassium through that exchange pumps, and that will involve so many ATP molecules. So that is less economical, and this is more economical because of the saltatory conduction.